Hi, Cliff. How's it going?
I'm good, thank you. How are you, Jamie?
I am excellent. We are having a great time here at .NET Conf this morning for me in New York. I know you have a lot to cover,
Yeah.
so we're going to be talking about remote computer science and PyTop, .NET, and Teams.
No, that's not me.
Wrong session.
Hope not. Anyway.
I was like, this is not correct, actually. Here we go. We're actually going to be talking about 3D printed bionic hand with IoT and Xamarin.
Yeah.
So perfect timing. I'll let you take it away.
Excellent. Hi, everyone, and thanks, Jamie and Jeff behind the scenes. My name's Clifford Ages. I'm going to talk to you about how I've gone about building a 3D bionic hand for a friend's son. There you go. My slides will move on. A bit about me first. My day job is that of an airline pilot for a major UK airline. So my office is the picture you can see there. I'm flying tomorrow on a long haul flight to the US. When I'm not flying planes, though, I'm a freelance .NET, Xamarin, and IoT developer. So I love playing with electronics. I love building things and tinkering with Xamarin and mobile apps and spending time with family and stuff like that. I'll come back to why I mentioned the fact that I'm an airline pilot a little bit later in the talk. But let's meet Kayden. Now, Kayden's a happy-go-lucky teenager. As you can see there in images, he's very active in the Scouts community in the UK and goes to jamborees around the world as well every year. But those of you more observant can probably see in the picture there that Kayden's missing most of his left arm. He's missing his left forearm, left hand, and on his right hand, he's missing all of his middle fingers. So he's just got his pinky and his thumb. Now, Kayden is provided by the NHS, the National Health Service here in the UK. So our medical teams and hospitals here in the UK is provided with a prosthetic arm. He's been part of a team that's been studying this, and he was provided one pretty much from birth, from about 6 months old. And he's grown up with wearing a prosthetic arm. But a lot of children don't get that privilege, don't get that chance, because these are expensive devices. Even these dumb ones that you can see here, which are literally just a claw which opens and closes. As you can see here, if I was to pull on this is literally fishing line. It opens and closes the grip. Now, as you can see there, Kayden's got this, and his party trick is to do that when he's on London Underground. He's off to the London 2012 Olympics there. But you can see the fishing line just coming off the arm. It goes across the back of his shoulders to a pad on his other shoulder, and as he moves that shoulder backwards and forwards, it pulls on the fishing line, and it pulls open the claw. And then there's elastic bands that pull it closed when he relaxes his shoulder. Every year, Kayden has to go back to the hospital. Every year, they take a cast of his arm, of the stump that he has, and they make that into a mold, which they then use to create his next new arm. And in typical kind of mum's kind of way of saying things, don't worry, you'll grow into it. They make it slightly too big, and after a couple of months, he grows into it and it fits. And just when it starts becoming tight, it goes back to the hospital and repeats the process. This process costs the NHS in the region of £4,500 to £6,000 every time. So they're not cheap. It takes a couple of days of Kayden's time and his family going back and forth to the hospital. So this is a picture of a prosthetic arm that was issued after the First World War. And you can see here, the design hasn't changed much. It's pretty much the same. It was a leather strap back then rather than a fishing line. And it just moved the forearm backwards and forwards. But this one is 100 years old. This is a picture in the Imperial War Museum in London. I took a few months ago when I was there visiting. So you can see here, the design hasn't moved on. Now we can do better than this. But let's see how good Kayden is with his prosthetic arm. Here he's making me a cup of tea. Us Brits, we love a cup of tea. So this is me recording him making a cup of tea. So you can see he's quite dexterous. You can see the strap goes across his back and his shoulders when he moves in a moment. You can see the strap there. And he's quite dexterous. He can pick up a tea bag. He can pull it apart with his finger and pinky. And you can see there he can make me a cup of tea. Now, Kayden's been, as I say, wearing one of these for a number of years. But we wanted to do better. So we searched the internet. Now, we start off with Google, Bing, etc. And we search around. And the first thing we come across on the NHS was links to the Limbless Association. Now, I've been giving this talk and been working on this project for a couple of years now. And the Limbless Association is still under development. So I think that developer needs to be given the hurry up or get a new developer in, I think. But what we come across was the Team Unlimited. Now, this was because there's a story on the national news in the UK about a dad that 3D printed his daughter an arm. And that's where this whole idea come from. So we found Team Unlimited. We printed one of their arms, not the Isabella. It was a slightly older version. So I started this about 2 years ago now. And that version we gave to Kayden. He tried it on and he was okay, but he felt we didn't give him any more than his hook that he had currently, because the fingers clasped, but it didn't do anything else. It just basically, he still had to move his shoulder. He still did the same job. So he wasn't very keen on it. So, you know, as a pilot, we're giving feedback and we take that feedback open and honest, and we don't sort of take it as negative. It's like, okay, right, that's where I need to improve on. So we went back to the drawing board, back to the internet, and I stumbled across the Open Hand project. This was a university project by Joel Gibbard, and he built a electromechanical hand, again 3D printed. It's quite bulky, it's quite beefy. The control wasn't very good. The 3D printing was a bit, as you can see, a bit edgy and bulky. But you can see there, he's starting to look into prosthetics, and the fact that biomechanical prosthetics cost upwards of $100,000. Joel then went on with others and created Open Bionics, which is a wonderful team based out of Bristol, where they produce these arms and they sell them around the world. Initially, Open Bionics was a open platform, and they produced or showed their designs on GitHub, and we all know and love GitHub. But because they were trying to get these sold into the likes of National Health Service in the UK and sold into markets in the US and Germany and France and places, for obvious reasons, they had to close the design because they couldn't have designs coming in and changing for the fact that they needed to get it quality marked and quality assured, etc. So they closed the design. But there's enough of a design there, and they put enough online for us to move on. So we go back to the slides. I downloaded the Brunel parts off of GitHub, fired up the 3D printer, and printed off all the parts there. You can see all the parts in white and red on my cut map there are all 3D printed. You can see the bags of screws and springs and dowels and things. They're purchased off the internet. And you can see the 4 Xamarin motors in the top left corner of the map there. So now we've got all the parts, we need to work out how to connect it to Kayden. So we needed to take his mold that he gets from the NHS. It's one of these, and we need to work out how to make the arm fit to Kayden, how he's going to connect to Kayden. So you can see there it was printed along, and you can see in the timer here, there's 5 hours and 45 minutes left of printing. So I went off to bed, as I normally do when I'm sending 3D prints, and come down in the morning to find the spaghetti's mess. The left-hand image, you can see the socket had popped off the print bed, and it failed to adhere correctly, and it popped off and it printed the left of the mess. But the middle image, it was enough printed for us to try. So we went around and popped over to Kayden and see his family, had a cup of tea, and we tried it on. And this one in the nursery rhyme style, this one didn't fit, it was too small. So we printed another one. You can see in the right-hand picture that was too big. So we printed a third one. The third one was just right, and it fitted like a glove. To the point where Kayden actually said it fitted better than the NHS one. Now, this 3D print, it does take a few hours. It's about 8-9 hour prints to get one to print, but it costs 80 pence in PLA plastic. 80 pence of plastic was what, $1 in plastic. So that's pretty darn cheap. When Kayden grows out of it, as he does every kind of 6 to 9 months, rather than having to spend days going out of the hospital and waiting weeks for a new one to be made, we just click print. Following day, he comes around after school and picks up the new one, screws it into the hand, and he's off again. And it costs us 80 pence. So, you know, that is kind of where we're going with 3D printing technology these days. So we look at the prices of all these 3D printed parts. Now you can see the top there is the molds that we use to put thing grips on. We'll go on to the next slide. You can see the black elements there are the urethane molds, and the reason is because the plastic that we print with is quite hard. It's like Lego plastic, and it's quite slippy, so you can't grip things. So we mold urethane rubber onto the end, which is the same sort of thing like neoprene and stuff that you make swimsuits out of. So we mold that on, and we use those molds. I've used those molds to make about 15, 16 hands now, and on the same mold. So that is a one-off cost of £10, $12. The actual interesting parts are the bits at the bottom image that we need to make. You can see at the bottom there, without the molds, they cost £5 sterling or $7 to make all the parts to make the hand. You add on the 80 pence or another $1 for the socket, and about $1.50 a pound to make the central part of the arm, which is different for every person. So obviously, where their arm stops is different for every child and adult. So you're talking less than $10. We've got all of the printed parts, all of the 3D printed parts. So already we're beating what is provided by the NHS many times over. So you can see here, this is the handy moving. He's okay with it, and you can see there it moving around. Now it works by, you can see the strings just pulling on the fingers, and as the string is literally a fishing line, Brady fishing line that pulls. So we're back to the fishing theme. It pulls via the motors, and it pulls the fingers in, and when it releases, the springs pull them back out again. How do we control it though? Well, Open Bionics, when they originally released this design online, they had the chestnut board. They had at the time, when we started this project, a store where you could buy the components that you needed. And the chestnut board always seemed to be out of stock. It was quite expensive. It was £250 plus VAT, which is our sales tax here in the UK, and postage and packaging. So it was quite expensive board. But at the end of the day, it was just an Arduino SAMD microprocessor, and nothing much else. So it was expensive and difficult to get hold of. So it kind of wasn't ideal. How do they sense to control the board though? Well, they use these malware sensors. And these malware sensors, as you can see in the image there, they use the little sticky pads. So if you ever have an ECG with your doctor, they're little sticky pads that stick onto you all over your body to measure the electrical signals your body's sending around. So these pads stick onto these boards. The boards stick onto the muscles, and if we look at where they stick, you need to stick them quite centrally on the muscle group to get a very good signal. As you can see the green signal there, the correct placement. If you stick it off place, like slightly higher, slightly too low, you don't get too much of a signal from it. So you need to make sure you put this in the correct place. Now, we could do that, but if you imagine giving this to a child, those boards are 35 to 40 pounds, so $40 to $50. You need 2 of those. The pads, a pack of pads to last you a month is $5 to $7. So they need to be changed every day because obviously they lose their stickiness. The child has got these expensive boards stuck to them. It's not ideal. It can break quite easily. So how does that malware sensor board work? Well, if you all grab your arm and put it up, straight up, and you put your fingers either side, just above your elbow, and if you do the close, which is where you pull your hand towards you, you'll feel the muscle at the back go tight. If you open out the other way, you feel the muscle at the front go tight. If you hold your hand straight up and you create a fist, you'll feel both muscles go tight. So all we do is we have open, close, change grip, and change grip goes to the next grip in the grip sequence. Fairly simple measurement. Now I realized that we could use that and come on to a different way later of how we measure those signals. That means that in the Open Bionics codes that they load into the Arduino board that they produced, and they've created 5 grips, which is better than what Kayden had. He had just 1 grip, open and close, and he can just pick things up. But now he's got a palm grip, so he can hold a bag, so he can help mum and dad with shopping. He didn't like that grip. He can have a point gesture, so he can point this over there to his friends. He can have an OK gesture, say OK. But he wanted more. He was like, well, this is great, but I want one to hold my Xbox controller, Cliff. Okay, we'll put that on the issues list, and we'll come back to that later. But how does it work internally in the code? Now, if we look at this array here, this is a 3D array that's held inside the code base. So if we want to add a new grip, we have to go into the code. So we have to fire up VS Code. We have to go in and edit the code. We then have to connect the board. So we have to take the hand apart, connect it to the PC, and load up the code. But you can see here, it's, for us as software engineers, we can work out what this does. But how about Kayden, parents, the doctors and nurses, the technicians at the hospital? We don't really want them editing code because, they can make a mistake and cause damage to the mechanics of the hands. But also, it's quite complex for them. They're not trained software engineers like we are. So again, I was ticking that up as a mental issue to come back to and try and fix later. So drawbacks we talked about, we've got a single source supplier of a board, it's often out of stock. The muscles, also those muscle sensors, as the muscle grows in strength, because Kayden's been using it, we need to get a jeweler screwdriver and change the little potentiometers on the board to change the gain values that are coming out, which again isn't ideal. The grip sequence, if he misses the grip sequence, he goes around that array, He's then got to remember, okay, I've missed the point one, so now I've got to go 4 grips again to get to the next one, and then it'll be the point one, which is the one I actually won. Wasn't ideal. Maybe he wants a different set of grips when he's at school from when he's at home. He doesn't want the Xbox controller grip when he's at school. So we're talking that as the drawbacks. He wants to try and fix and push back into the Open Bionics project. So how do we fix the first one, the controller? I use these Adafruit featherboards in a lot of projects that I do with IoT for clients. The Adafruit system's fantastic, based out of New York. And this featherboard system they have, they're all the same form factor, and they just have different areas. You can see at the bottom right there, the red board, that is a Bluetooth sensor. You can get one with Wi-Fi, you can get one with LoRaN, which is a radio frequency. You can get one with GPS. They come at all different sizes, but the actual pin out and form factor is identical. So I got a few of these. I got them from Amazon just to prove the point you can get them anywhere. They were delivered next day for less than £20, less than $20. Next day, the postman was knocking on my door and delivering one of these. So they're fantastic. Got a built-in battery charger, LiPo battery charger. So lots of things to chalk up. It's like, these are brilliant. Let's go with one of these. So we built one of those. We added on the Adafruit also make a motor controller board. You can see that the other board that's there on the image, and we use that to control the motors. Initial problem was the fact that the motor, the cable, the flat ribbon cable that comes from the motor is a flat ribbon, and we've got through holes, so we need to find a special connector. We managed to find one of those and solder that into the circuit, such we had it working. Now we need to load the software. Now, anyone that's used Arduino knows and loves the Arduino IDE. It's effectively Notepad-esque IDE. It's not very good as an IDE. It's not as full-featured as VS Code and Visual Studio, the weird software developers know and love. It's more of a hobbyist IDE. VS Code is really good for programming Arduino, but it uses the Arduino IDE under the hood, and you can't debug still. With Visual Studio, we know and love F5 and F9 for debugging and making breakpoints. And if you use this Visual Micro add-in for Visual Studio in the store, you can add in and control and burn your code down to your boards. Also, you get debugging back, so it's awesome. I can't highly recommend this enough as an add-in for Visual Studio if you're going to do any IoT development. So now let's get onto the muscle sensors. I was flying along. I remember it quite vividly. I was off to Japan. I was somewhere over Russia, and I take magazines with me to read in the cruise when the autopilot's engaged. We often have something to read, a Kindle or a magazine, and we'll read a bit of an article and look up and make sure we're managing the aircraft correctly. And we also make sure that someone's flying the plane and the other person can relax for 10 to 15 minutes. And there's an article about Arduino debugging, and we noticed this sensor in the bottom here, which is I've not drawn that very well, but a piezoelectric sensor, which basically is using in tiles, it's using in explosive demolition, and basically it measures an input. So if you hit it or bang it, it gives you a small voltage out, which you can measure as a signal into your Arduino board. I was intrigued, so I got to Japan, ordered a bunch of these, and for less than £1, I had 10 of them on my door the following day, waiting for me for when I got home. But we tried it, and Kayden wasn't happy because he couldn't stop the hand mid-flow like he could before with the malware sensors. Okay, we'll go and look for something else. So then we come across these force-sensitive resistors. Now these, as you apply pressure, they give you a different resistance. So you send a voltage for it, and you get a different voltage out. You can measure that. Excellent. Now we've got force-sensitive. These are £6 for a pack of 2. So rather than the £35 each for the malware sensor, we're now down to £6 for a pack of 2. We could stick those quite happily inside the inside that 3D printed socket that Kayden slides his arm into, and now we can measure, because the muscle goes tense, it pushes against that hard Lego type plastic, and we can measure the signal coming out. It's awesome. So now we solved that problem. So drawbacks then: single source supply from the board, often out of stock. Adafruit and the derivatives of lots of other companies are copying their design now. So we're quite safe in the fact that it's not going to go anywhere. We get from Amazon. The muscle sensors, well, we've replaced those with these force sensitive resistors. Again, I bought them from Amazon just to prove a point, and there's many manufacturers of these, all different shapes and sizes. So that's good. So now we're down to the grip sequences. Miss it, you go around, you want to make your own grip. Okay, well, what can we do about that? Well, I said earlier that I'm a mobile developer and I love Xamarin. So I thought to myself, well, I've got this board, it's got Bluetooth on board. I can write a Xamarin app, and the Xamarin app can access the Bluetooth stack. So I can write this app that access and sends data to and from the Arduino board. It's in the back of the hand, and I can write an app about it. So I was like, this is excellent. So this is what we went with. So just a little bit about Xamarin Forms, just in case you haven't seen any of the other fantastic talks by Maddie Legier and David Ortnow and others on .NET Config. Not go back and watch them, but very quickly, you got two versions of Xamarin. You got the traditional one where you build your own UI layer, and it's all C# backends, or the one that I'm now leaning towards and favor is Xamarin Forms, because it's moved on leaps and bounds. It's no longer really the forms bit should disappear. It's no longer just for that business layout form. And some amazing apps have been developed using Xamarin Forms and the shared UI. So I write the UI layer in XAML or in code, and it will share and look as it needs to look on each of the different platforms. So that's what I did. So if we bring across the Handy app, so this is my my phone sitting in front of me. Here's Handy. So we can see Handy here. So if we open the app, you can see it takes a few seconds to boot up. And we open up. It says connect first. So if we connect that and we plug the battery in and start scanning, we can see Handy appears in the Bluetooth. It's now connected. So now we've got Handy connected. And if I go across to, or I'm quick enough and go across to the UART control, you can see the fact that the two are communicating in the background over UART. And this is used for advanced features on Kayden and his family's version of the app. They don't have this functionality. It's just for me as a debugging. But if we go back to the grip selector, I can now push the big button and close the hands. I can open the hands. I can move to a different grip in the grip sequence, and I can add them to my favorites. So I can put them onto my favorites and add them into the list. I can go to the grip order. Maybe Kayden wants his grips in a slightly different order. So he can change the grip order, save it down to the hand. So now when he goes around the grip sequence, it's a completely different grip. It's going to remove the battery for the moment. That whining, if you can hear it over the speaker, is because I've got two dogs. And when I'm testing, if I leave it running for too long, they start getting upset at the high-pitched voice sound. So I've tuned it down so it's out their audible range in hours. And they're not so upset and they don't go barking at me. But the other thing is we can do a grip builder. So we can make our own grips and save them to the hands, which is fantastic. He can now make his Xbox grip and add it to his sequence. The other things we can do is we can go into the settings. We can change the settings of the hand, if it's a left or right hand. We can change the hold and peak threshold, which is settings within the hand for that timer that runs round. And also we can change the way the muscles and that work. So this is the sort of thing that the technicians and the doctors and nurses would need to change at the hospital. But also we can do a muscle sensor check. So every week or two, Kayden runs into this, he starts it and he runs through what we tell him to do, which is open, close his hands and try and get these bars, these two bars here, that one there and that one there. Try to get them to the top and hold them for a second or two and release them again. We then send that data for processing. It goes up to an Azure function, it gets put in blob storage, and we're collecting that data. We've been doing this for a number of months now, and at some point in the future, we're going to get some machine learning to reason over that data and then change the values that are in those dwell times that were in the settings to save him having to go in and change it himself. So we come back to the slide deck. Kayden's now got his Xbox grip. He's over the moon. He just needs the new latest Xbox. And not the old one. He's waiting to get one here in the UK. Santa's not too far away, but we've got an Xbox grip where that trigger finger just twitches. So as he twitches his muscle, he can twitch that in and out. So he doesn't need to completely open and close his arm, but it just moves that trigger finger, and that's fantastic. He's over the moon. He can now play his Xbox without needing the adaptive controller that Microsoft produced. So now let's look at the cost then. So all the parts, the 3D printed parts, as we said earlier, come to 10 to 15 pounds, everything, that's the molds, everything. But all the other parts we need to purchase and buy literally arrive, and they cost just over 500 pounds. So what, $680. So the National Health Service is spending 4,500 to 6,000 for a fiberglass arm without the hook, I might add, because that's a few thousand more. The hook is interchangeable and he gets that moved to the next arm as he moves along and grows. So just the fiberglass part that's made. I'm managing to make this for just over £500. Obviously, there's none of my time in there and the software and the bits and bobs behind. This is just pure mechanical parts and the software. But you know, I've written a software. It's on GitHub. It's open source for anyone to go and download and play with. That works on the Adafruit board, not on the Chestnut board for Bionics. And that I'm planning to open source the app as well, as we get it to a point where it's usable for all. But the app and everything else, it's, you know, it's there and it's super cheap. So what's next then? Well, I want to finish off building a mobile app out. The version that's on my GitHub at the moment, that's open source, isn't the version that's on Kayden and his parents' phones, purely because there's some personal information in there that we don't want to share on GitHub, and we want to be very careful about what we're sharing here on the data we're collecting and how we're collecting it. So once we've got it to a point where we're happy, we'll desensitize the app and then push it up to GitHub again in the open source version. We want to get machine learning to reason over that data and send the data back to the app, so that when he arrives home from school and he turns his phone on, the app gets the new push data, and he connects his arm and it will connect up. We'd like to go full .NET, which I'll come on to in a sec. But also we're moving on to prosthetic legs. We've realized that actually this 3D printing stuff is quite cheap, and we want to fix the problems with legs as well. And that's because my uncle recently had to have a leg amputated for medical reasons, and we'd like to replace the leg that he has, which is pretty much a stump. Yeah, we'd like to fix that as well for him. So moving on to full .NET, not sure if you've seen it, but you got the Meadow Micro F7 board, which is the same form factor of the Feather board, but it runs full .NET and the mono runtime. These are slightly more expensive, about twice the price, but it's .NET, which means we can do a lot more machine learning on the board rather than in the cloud. So that's bringing IoT direct to the edge. So that is absolutely fantastic. And I do have one here, and we're trying to get the software to work on there and control the motors and get it working. So why did I mention being a pilot? I just said at the very beginning, the idea behind this project, quite soon after we was doing this and I started giving talks, people were very interested, and people around the world were very interested as well. So what I want to do is put a 3D printer. I was hoping to do it this summer, but obviously COVID has stopped that. Put a 3D printer and some parts into a box and a couple of spools of filament, take it somewhere around the world where they don't have the wonderful NHS or health services that, you know, Europe and America tends to have. Take it somewhere, go to a hospital, drop it off, show them how to use the kit, and then pop back a month later and see how they're getting on, and be on the phone or team or Skype call later on to help them out, so that they can give back to the local community, because they may not have $4,000 to $6,000 to produce these arms for children locally, whereas we can produce it, you know, much better device for much less money. If you want to jump in, you can find me on GitHub. It's GitHub/CliffAges, and you'll find all the handy parts in there. You can jump in and help out. That's it. Thanks for joining. I just want to say a massive thank you to Kayden. He's been fantastic with the feedback. He loves his arm. He loves playing his Xbox. To Kayden's family as well, that test out the app as well. They get a push from App Center every time I push it to GitHub. They get a new app update from App Center. They love it. They give me feedback on WhatsApp or via App Center. And also massive thanks to all the behind the scenes people here at .NET Conf that are helping out, that I don't think get enough praise. So thank you, everyone. Thanks a lot.
Amazing. Holy cow, that was phenomenal. Thank you so much, Cliff, and thank you, Kayden, and your family. It looks like you're doing well, and we're so happy for you. We're a bit right at time, and we didn't collect any questions for this session,
Okay.
but yeah, it means you answered everyone's questions without fail.
Well, if they want to question me, they can reach out to me on Twitter, so they can find me there.
Perfect. So everybody, please go and do that. Ask all of your amazing IoT questions to Cliff. Thank you, Cliff, for joining us. We really appreciate you, and we'll look for you soon.
Bye now.
Take care.